exam Q&A?
No, just testing.
Oh,
We're just testing that Julian can go live, then transfer me the host so that I can actually
oh, hi, Matt.
Hello.
Good morning.
do the thing.
Oh, hi, Mark.
Can someone go and just check if the YouTube channel is streaming?
Yeah, give me 1 second.
And go on.
We are.
I can confirm it is.
Okay, so it's live right now.
I'm going to make you host,
All
Anson.
right, now Julian's going to make me host, and let's see if it goes tits up.
Probably.
Make host. Do you want to change? Yes.
Okay, are we still live?
There's a bit of a delay, but it hasn't gone wrong yet.
Okay, we'll just wait for the delay to be over.
Yeah, I think it is. We're in business.
Are we all good?
Give it just a moment.
Fabulous.
Yeah, it's working fine.
Okay, so we'll just leave it like that then for the rest. Like, we don't mind streaming the Q&A session. It's going to make very little difference. Shall we start letting people in? Is there anything else we need to discuss?
Shall I click admit all?
Do you want me to put something?
Is it worth pinging across a little email saying, morning, time to join?
Good morning. Join this Q&A, please.
Yeah, Matt, do you want to put something in the Discord? Morning, Dr. Carr. I hope you got my 2 emails.
Yeah, morning. I'll send you a quicker solution to question 7 as well, just in case anybody does it a different way.
Okay.
Yeah, looks fine. Thanks for all your work in getting it ready.
No, it's okay.
And sorry for the flurry of last-minute things last night.
Yeah, I know. Yeah. Oh, by the way, we also have one more team. We've gone up to 47 teams.
Joking.
Excellent.
Did you resolve the issue with someone asking about joining without a team?
Yeah, basically they're not a participant. They were just here for but because we said participant, they were like, "Oh, do I need to be in a team?" Yeah, but then no, we have actually gained another team. Yeah.
That was why I did post in the Discord, just something to always be aware of, and feel free to vocalize when we are chairing the talks that the public are available, that, there are sort of non-planks directed communications and planks directed communications. We need to clearly signpost that stuff that is for planks is not for the members of the public, and that they don't need to worry, basically.
I've just told everyone in the waiting room, morning, we'll let you in very soon. So whenever anyone's ready, I'm ready to go whenever. I'm gonna make this stuff up.
Likewise, yeah.
Should I press the button?
Do it.
Yeah, press the button.
Too late.
Bam.
Boom.
In they come.
Good morning.
Actually, Molly, if you take off the slide for a minute, and then we can just wave to everyone and see everyone and say hello.
All right.
Morning, everyone.
Morning.
Oh, there's a lot of you.
And so you got a lot of questions to answer.
I hope not. I hope we made it all very clear and very straightforward. Announcements. That's not. Oh, that's Matt. General Kenobi.
Or a bold one.
I don't know where my. Here we go. Exams information. That's good. Oh, more people.
Recognizing names of people that I played games with last night. Getting to know you all. I'll know all 200 names now. I can aspire to.
Good morning to everyone that's joined us. Morning.
The time to think about playing some lift music.
Yeah. Right, let's see what we've got in the collection.
Anthony managed to play the countdown music for the quiz last night.
I'm slightly concerned that you said lift music, and the first thing I thought of was Flight of the Bumblebee. That's the least relaxing. Can you imagine if that was the lift music going up anywhere? Extreme levels of stress in the morning.
Yeah, you don't need that at 9:05.
Get them ready for the exam with all their stress.
Everyone's
Oh,
like,
what's the song that just goes, "You've got to pump it up"? That's a song, isn't it? I think all the entire lyrics are just "You've got to pump it up."
Anthony, you're showing your age here.
I've used that as a quiz question, I'm pretty sure, but maybe Cats were saying it.
You've used everything as a quiz question.
I have used everything as a quiz question. It's okay. Make new stuff so I can make new quiz questions. Oh,
Anthony, do you want to remind people of how they need to rename themselves?
yeah, I will do that, and I'll do that before Dr. Price's talk as well. Can you please make sure that you rename yourselves as your name followed by your team name in brackets? So actually, all of the organising committee, can you please rename yourselves as well?
Yeah, I did that yesterday, but
So
I'll rename you guys. Don't worry.
Anthony, Molly can do it for me. How do we do that? Well, you go to your you go to your icon under participants. You find yourself, or you can click in the top right little 3 dots on your name, and you go click rename, and you should be able to rename it there. So,
Oh wait, I can't rename you because I'm not the host. I'm only a co-host. Anthony,
I have to
everyone
rename
have to rename
myself. Oh, hang on, rename. So yeah, if you go and either go onto participants list, scroll down, find yourself. I think you should probably be at the top. Click on the more button, and you can rename yourself. So find on your icon the 3 dots, and that should do it.
Thanks, Sam.
And
Joe and Matt, if you put the same as me and Anthony. Anthony, why you got to put it in brackets for?
I just want to be consistent with all the teams that I've asked to put in brackets.
You can say it in brackets.
I need the team. Oh, the team list is on this one. Okay, we'll give it. I will give it to 10 past. Like the exam Q&A, it's not really. It won't. It wouldn't. It wasn't going to take half an hour. And we knew that everyone would be incredibly tired after the fun activities from last night / just normal life, and didn't really want to get up, and neither did we.
I mean, feel free to drop any questions in the chat also about
Yeah,
the
you
whole
can.
weekend. If you have any, also I can answer those while Anthony answers the same question.
I need documents. Downloads.
I like reading all the team names.
I don't get up at 9 for my lecture.
Well, you're
Um,
here, so it must be worth it, right?
You know, if this was a normal planks, you would have been up, you would have been fed, you would have been watered.
Yeah, just be glad it's online.
Last year we trudged through the snow at this time. Well, in fact, we trudged through the snow by this point. Back in my day, we walked at least.
Oh.
We waking up on Saturday at this hour is a crime against humanity. So are exams, but hey ho.
It snowed, did it? Or it sleeted? It was absolutely wow.
It snowed because when we were going for the bus after the exam, there wasn't any spaces left on it, and we got absolutely covered in snow on the way to the restaurant afterwards, to the cafe after the.
I remember seeing in your vlog.
Yeah.
Yeah.
I was frozen despite wrapping in many layers.
Like,
Yeah.
fun.
wasn't fun.
I love that. Post a SpongeBob meme and I'll make you win the exam. No, I'm just kidding.
Oh, these are great. These are great.
At this
Oh,
time,
yeah.
2 years ago, we had to travel from London to Surrey by this time this morning.
Yeah, you're right, Dr. Carr. Anthony really is 132.
But
Showing your age.
the reason Anthony is so versed in quantum mechanics is he was actually there for the,
For the discovery.
conference in 1923 and 1926
This is
when
just mean. Like, hang on, I can mute people actually, and you can't unmute yourselves. What's your secret? Not sleeping enough, probably.
oh wait, are you the person that keeps doing the doctors will hate this one trick that'll keep you
Yes.
young forever
Yeah,
advertisements that I keep
actually,
getting online?
the infuriation and the hate of people trying to close those adverts is what fuels my life. Yeah. Shall we get
Is it-
started then? Molly, would
Yes.
you put up your slide, please?
Shut up,
Yeah, I
Molly.
think Dr. Price has also joined us as well. So good morning as
Good
well.
morning.
Hey,
Hi, Hannah.
hello.
Hello.
Can you see my slide?
Mm-hmm.
Fabulous.
Right. Exam question answer session. So I'm just going to read through the rules and the format of the exam. Should take 5 minutes. So I'm just going to read them off this list here so I don't miss anything. And then feel free to ask any questions that you might have. If not, we can sit in silence until Dr. Price's talk starts. What are the questions? And the
Really?
questions are physics questions. Yes, mainly physics questions. Yeah. Anyway, right. The exam is going to start at 10:30, and that will be directly after Dr. Price's talk. And you're going to have 2 hours for the first half, as it shows on the slide. Then there's going to be a break for half an hour where you can go off, have lunch, or go get a cup of tea or something, or just, relax for half an hour. Go stretch your legs. Don't look at a screen for half an hour. It would be nice. And then there's another 2 hours when we come back at 1. and then the exam finishes at 3. So at the break time, I'm going to close all the breakout rooms that you're in, so everyone comes back into the main chat so we can announce any corrections. And then also at 3 o'clock, the breakout rooms will also close because you shouldn't be collaborating anymore, and you should only be submitting the questions that you've got on the website. You will be given... You know what the answers are. Stop it. Dr. Carr. What was I saying? Yes. So once we get to 3 o'clock, the breakout rooms will close. You'll be given plenty of warning, and then you have half an hour to submit them. And all the submissions, all the exams, all the information can be found at the website planks.uk/Kent-exam. And you'll be able to download the paper there. As soon as you are put into your breakout rooms, the exam will go live on the website. At least one member of your team should always be in the exam, in the Zoom call at any one time. There will be invigilators going through and just checking, seeing how you are throughout. Usually do that within the first 20 minutes. And we'll do that after the break as well. If you do have any questions during the exam, either come into the main Zoom call from your breakout room or use the fun raise a hand feature, and someone will come and find you eventually. That someone's probably me. When uploading, please submit each question as a separate PDF. So all your work that you've done for question 1, scan it in. Make sure you label each of your written pieces of work with your team name and what question it is, just in case some technical mishap happens and things go crazy. You want to be able to still get the marks. So please submit each question as a separate PDF. So when you click, if you go onto the website, you go to upload folders, you'll find your team name, and just there should be 10 PDFs in there in total. As I mentioned, during the break, we'll announce any clarifications. I will also send out a live broadcast message on Zoom, but hardly anyone ever sees them. So just be aware that there is a folder, there is a file folder thing on the website, and just check that maybe every 5-10 minutes in case there's anything that's been announced. You are not allowed to use external resources during the exams. That's textbooks, searching on the internet, lecture notes, etc. People that aren't in your team, please don't. For certainly some things, it's very obvious where you haven't fully attempted the question. You are, of course, allowed to use not programmable calculators, scientific calculators, watches, medical equipment. And for this exam, you may use a tablet or digital writing device to write your answers on and submit as a PDF, rather than just writing on pen and paper. Please don't upload photographs. Just don't. PDFs only, please. Thank you. And then, of course, if it is brought to an invigilator's attention that a team has been cheating or breaking the rules, and that's all the rules, including the IOP and IAPS codes of conduct, the team may be disqualified, and disqualifications can happen post-submission. And of course, in situations where no rule applies, the committee will roll on the matter. Now that I've gone through all that jargon, I think there's one other thing. We didn't announce it yesterday, but we'll tell it to you this morning, and maybe I'll say it just before the exam starts again. Sorry. Because, usually what happens each year is we get to send teams off to have a very nice trip to some place, and the IOP pays for the expenses and everything. This year, because that is not possible, and because there is only one team going to represent the UK and Ireland at the international finals, we have decided to give a monetary prize, much like the international finals, to the first, second, and third place team. So the team that comes in first will receive £1,000 between them. The team that comes in second will receive £500 between them, and the team that comes in third will receive £250 between them. Okay, so that's it's something a bit nice, and we're very thankful, grateful to the IOP for doing that. It was very nice of them. And of course, the winning team will go on to represent the UK and Ireland at the Plankathon, not the first edition of online planks. Well, we were the 0th edition, I guess, for the finals last year. Okay, I think that's everything that I wanted to say. I don't think there's anything. Oh yes, someone brought up quite a good question yesterday. What to do in an emergency situation. If your room is on fire, please leave it. Don't bring the exam with you. If your fire alarm, like in university accommodation, is going off and you have to go outside, go, please. And maybe one of your teammates can let us know. If your Zoom breaks, your laptop implodes or something like that, please do message me. You can either message on the Discord, I will have that open, or email at kentplanks@gmail.com, or you can get one of your other teammates to get my attention in Zoom so we know what's going on. Yeah, I think that's everything. So if there is an emergency, don't worry about the exam. It's only an exam. It's a very fun exam. Okay, should we just go through the list and see if there's any questions in the chat? What's your secret?
We have one question about someone has a team of 3, but one teammate can't attend, so they're down to 2 people. Is it still okay that they're?
I see no issue with you continuing with the exam, but just know we won't be more lenient on you or less lenient on you, and you've probably got more work to do. It's unfortunate, but that's the way it is. If you also just make yourself aware, and we'll make a note of that as well, and tell us which participant can no longer attend. Right, any other questions? If you leave the Zoom call, do you automatically get added back into the breakout room? Yes, but sometimes people have technical issues. So I did ask in the in the latest email that I sent out to all participants that you make sure your Zoom is the most up to date that it can be. If you do leave the Zoom call and you don't get automatically put into your breakout room, when you come back in, I will just assign you back into your breakout room, so it should be fine. Any other questions? If all teammates are physically in the same room, do we all need to log into Zoom? No, you just need that one. You just need one person logged into Zoom. So there's we have situations where people live together, or they've managed to get a study room all together because they're in their whatever bubble. So yeah, you only need one Zoom, but make sure you stay on that one Zoom throughout. Yeah. So everyone, just please make sure that you rename yourselves to have your name and your team name. If I only find one person and then their team name, I will know that it's all 4 people, 3 people in that team, and you'll just go into a breakout room on your own. Okay. Any questions people want to shout at? Pro, don't actually shout out. Maybe speak or put in the Zoom chat or whatever. What did you have for breakfast? I had a cup of tea and 3 Weetabix. Is there anything stopping us from collaborating using virtual whiteboard environments? No. People did use this in London, and they seem to say it worked very well, providing the collaboration is just between your own team. So is it just one exam, but we take a break midway? Yeah. You can attempt the questions. Whenever you get a Planck's exam, the first thing I always do is rip the pages out of the booklet, because everyone wants to. Usually you get one booklet between 4 people. Yeah. And then you always have the situation where someone's got half a question on this side and half a question on that side, and you have no idea what's going on. So yeah, you can attempt the questions any order you like. It's perfectly fine. Right. Would you rather meet Newton or Einstein? I don't know. I'll have to have a think about that one.
There was a more important question, Anthony. Did you have beans or milk on your Weetabix?
I had milk. I arrived a little late, sorry, has it already been asked, but no uploading pictures, please. If you're going to, please scan in your written work and submit as a PDF. So you might have a scanner. Most phones can now do scanning in.
You can use Cam Scanner, and then it emails. You can email yourself the PDF.
There you go.
10 out of 10 recommend.
But yeah, we don't want anything other than PDFs being submitted. Thank you, because this is Google Drive and Microsoft. Oh, there you go. Someone's sorted it for you. Handwrite for sure, but use scanner software rather than the pic. Yeah. Oh, yeah, it's Dr. Carl. Yeah. Someone to be admitted. Yeah. If that's it, then or if you think of anything in the next 8 minutes, please do. If not,
a reminder to please put your team name in brackets after your name.
Yeah.
So that Anthony's job is a bit easier.
Yeah. Just so you know, we have 47 teams competing today, which is the largest number ever in Planck so far. So I think there's 180 participants. So absolutely fantastic. We never expected it to get this large, especially considering when we originally started planning this, one of the accommodations was going to close down. What's this? Anthony, what does this say? Anthony, you look like you know things. How do I calculate the gravity of a situation? Use your best judgment. If we want to, are we allowed to work on the test during the break? No. It's a break from the exam. So the exam, we can't stop you. Yeah, but you shouldn't be. And that's the reason also why the breakout rooms were closed, because there shouldn't be collaboration during it. But, Can't stop you. Yeah. I think it's also quite nice having the break because you might want to go off and use the bathroom during your 4-hour exam time, and then you've actually got a bit of wiggle room there to actually have 4 hours to attempt it. For sorting out the Zoom, do we need to stay into the call until 10:30? Yes, please do stay for Dr. Price's lecture. It sounds incredibly interesting. I'm sorry, I'm going to be slightly distracted throughout it. I'll have to watch the recording. But please stay in because, as I said, the exam will start at 10:30 and we will not extend the exam or anything like that. It will start at 10:30 and that's it. Okay? So, yeah. In your solutions, make sure you, yeah, good. Can different people re-upload different answers? Yes, so you can continually re-upload until 15:30, in which time it's done. There's no more submissions being accepted. Unless there's something has gone absolutely wrong, in which case, please bring it to our attention by coming into the main Zoom call, as we did have last time. Okay, what was I doing? No one say anything else? If we have questions during the exam, yeah. You might not have been here at the beginning, but if you have questions during the exam, either come into the main room, or you can use the raise your hand feature, and an invigilator will come. Molly, I think if you click to the slide after the next slide, because I think the next slide is Dr. Price's talk, and then I've listed a few key things here that you can always just come in here and see. If there's no one in the main Zoom call, that's because they're dealing with someone else. But you can either wait there or use the raise your hand feature and we'll come to you. Okay. Most welcome. Anything else I want to say? No. James, did I miss anything?
So you covered everything quite well.
Okay.
I think. Any other questions?
Yeah. As I think I said yesterday a bit, the Planck's exam is not like a normal physics exam. The questions are written that anyone who has done any part of university physics can attempt them almost perfectly. I'm sure, there helps with practice and age. But any first year should be able to attempt any of the questions put in here. Where, as James always says, we like to write the questions self-contained. So all the information needed in order to attain the full marks is in the questions. The rest of it just relies on basic physics knowledge and some logic. So, if you see the question, it looks absolutely horrific. Take a step back, think about what you do know, and it might actually just come out easier. And we do always reward creativity, because there's not always one answer for a question, and sometimes it does come down to the most creative answer gets a higher mark, and that can determine between first and second place. So, yeah, think creatively, enjoy yourselves, throw some paper aeroplanes, etc. I'm sure I'll mention this all again just before we start the exam, but I'm going to stop talking now. Do answers? Yeah. Well, if you're marking, then I guess they do.
Most importantly, remember to have fun during the exam.
Yeah. I think someone put in the quiz last night. Throughout it, they gave me an update of how much fun they were having, and then at one point they said, "At this moment, I'm not having fun." So they actually got a negative mark, because I did say failure to have fun will result in a penalty, and it did. So right. I'm going to stop talking now and hand over to Molly, Joe, and Dr. Price.
Thank you. Just going to wait just a moment. We've got more people, a lot of people joining at the moment. Okay. Yeah, so good morning, everyone. Welcome to day 2 of Planks. We're very excited this morning to have Dr. Hannah Price giving us a talk before your exam. So I'm going to hand over to Joe in just a moment, but I would just like to welcome all the participants, firstly, and anyone external from participating in the competition joining us. It's great to have you. We're really happy that we're able to extend these talks to the public and get other people involved. So if you've heard about this, either through outreach or through IOP correspondence or, just word of mouth, then we're very happy to have you. And if you are not already a member of the IOP, I definitely recommend that you become a member of the IOP. You can attend more events like this, and the membership benefits include much more than just attending these talks. So I would definitely recommend that. But for now, we'll start on with this talk, give you a taste of what else you could have. So I'm going to pass over to Joe, who's going to share this wonderful talk. And yeah, I hope you all enjoy.
Thanks very much, Molly. So yes, as our chair for the weekend has just stated, our second talk is being given by the exceptional Dr. Hannah Price, and it is entitled Exploring Topological Phases of Matter. So a Royal Society University Research Fellow and a reader in theoretical physics at the University of Birmingham, Dr. Price received her PhD in the theory of ultra-cold atomic gases in 2013 from the University of Cambridge. She then moved to Italy, first as a postdoctoral researcher and then as a Marie Curie Fellow at the INO-CNR Centre at the University of Trento. In 2017, she returned to the UK and formed her current group at the University of Birmingham, which focuses primarily on investigating topological phases and dimensionality in photonics and cold atoms, using techniques like topological pumping and synthetic dimensions. And in addition to this crucial theoretical work, Dr. Price has also managed to experimentally investigate 4-dimensional behavior of the quantum Hall effect, being amongst the first in the world to do so. In 2018, she was awarded the IOP James Clerk Maxwell Medal and the prize for her early career contributions to theoretical physics, and she has kindly agreed to provide an introduction to a fascinating work. So please take it away.
Great, thank you very much for that kind introduction. So I will start sharing my screen. I think you need to allow me to share my screen, I'm afraid. Now I can, fantastic. Brilliant. So please do put things in the chat. I am not going to be able to keep an eye on the chat and focus on the talk, so I would ask the chair to feel free to interrupt me at any point with any questions or requests from the audience. So if you have something that you want clarification about as I'm going, then please do put that in the chat and the chair can bring it to my attention. Okay, so I want to give you today an introduction to a field of research called topological phases of matter. And the reason that I chose this is both because I work in this area, but also because it's one of these hot topics in what we call condensed matter physics. So I know that there's quite a broad audience today, so I'm going to try not to assume too much knowledge, but I'll throw in some things for those of you who are also more expert in the field. I do apologize to those experts because I will be making simplifications to give an accessible approach to the subject. Okay, so topological phases of matter. What on earth am I talking about? Well, the difficulty of explaining this field, I think I can show you by first highlighting some of the headlines that were published in newspapers following the award of the 2016 Nobel Prize for Physics that went for the subject of topological phases of matter. So this was a Nobel Prize that was awarded to Thouless, Haldane and Kosterlitz for the work that they had done to bring topological ideas into physics. And unfortunately, one of the parts of there being a Nobel Prize is that then the media has to tell everybody about it. And so people had to come up with headlines. One of the headlines was Bagels, Pretzels and Buns, everything you need to know about Nobel physics. Another one from the Telegraph was slightly more confused. British scientists win Nobel Prize in physics for work so baffling it had to be described using bagels. So you can tell that people are not really getting to grips with this subject. And Wired was my favorite because it just gave up completely. And it said Nobel Prize in physics goes to another weird thing that nobody understands. So that is unfortunately where I'm starting. So I will try to explain to you by the end of this talk some of the ideas of what a topological phase of matter is. And I'll try and do a better job than these journalists thought they could do in these newspaper articles. But I'm going to start at the same place, and that's the bagels, the pretzels, and the buns. So that's also the picture I had a slide ago. I had this beautiful, delicious looking pretzel. And what has this got to do with anything? Well, the reason that we start here is because it's easier to understand what topological means by starting from mathematics, where we can think about the topology of surfaces. So topology in mathematics is a way of, for instance, classifying and grouping different surfaces. So you may have heard the old joke that a topologist is somebody who cannot tell a coffee cup from a bagel. And the essential idea here is that the topology, according to topology, these two things are the same. So in a nutshell, mathematically speaking, we can think about topology as being concerned with properties of a surface, for instance, that are preserved under continuous deformations. And by that we mean things like stretching or twisting, rotating, crumpling, bending. So anything that you can do that kind of like stretches or smushes something together, but not a discontinuous deformation, for instance, that tears a surface or glues it. So somebody's actually done a lovely version of why is a coffee cup the same as a bagel, printing out each stage of this transformation. So the idea is that we can go from a coffee cup all the way to a bagel just through the allowed types of continuous deformation. So you can see here that what you're doing is you're kind of pushing up the bottom of the coffee cup and pushing it up and up and up and stretching it out till all you're left with is that hole through the center of the handle, and that is what gives you the bagel. So topology is a way of grouping and classifying stuff. So let's say that you want to organize your pastries and baked goods. So you start with your bagel, and okay, you've only got one thing at the moment. So a bagel is one type of object. And then you say, well, I want to know if this pretzel is the same as my bagel in a topological sense. So, have a think about that for a second. And I'll remind you about the definition. So what are we allowed to do? We're allowed to do anything like stretching it, twisting it, rotating it, crumpling, bending, but we're not allowed to tear or glue it. Well, then by that argument, you can see that this thing has got these two holes, whereas the bagel only has the one hole. So you can't go from the two hole to the one hole in a continuous way. So that's got to be a different type of object. So it's in what we call a different topological class. And then you can get something like this. So this is the picture I had at the beginning. And you can see that this has got three holes. So that, of course, has got to be something different again, because there's that extra hole that we can't get rid of. And so these are three examples of three different topological classes. And so we can say that everything in the blue box are all of the items with one hole. Everything in the orange box is where we put all of the two hole things, and you can have quite exotic things that have two holes. Then the three hole objects, the surfaces, all go in the purple box. And you could keep going, 4, 5, so on and so forth. And so essentially this is something you may have heard of called the genus. And it's an integer that we can associate with these different families. And you can see some essential properties here. So it's an integer, which means that it's something that is not possible to smoothly, continuously change. You've got to jump from 1 to 2. You can't go 1, 1.0001, and so on and so forth. You can't smoothly go between integers. You jump between these integers. Because of that, it's robust. So robust in this sense is topological robustness. So anything that we do that smushes and stretches is fine, but we can't tear or glue. But that does still allow for many, many different surfaces to all be grouped together. And the other thing I want to emphasize about that is that it's a global property, because you have to look at the whole surface to know how many holes there are. If you just look at one part of a surface, if you just look at, for instance, the one part of the mug, you don't necessarily know that there's a handle. You've got to look at the whole thing to see that there's the handle. Okay, so bear that in mind. So essentially, the message to take away from the bagels, pretzels, and buns is that topology is a way to classify different types of objects, and associated with it, we have the notion of topological invariance, and these are robust global integers. Okay, just one thing finally to say about that. If you go on Wikipedia, you can find this video of someone imagining a topological transformations on a cow, and whether or not a cow is has got the same genus as a bull. I'll leave that one for you to think about and discuss. Okay, but why should we be talking about topology in a physics conference? Why do we as physicists care? Well, we care because we like to classify things and we like to organize things into different families. And in my title, I had this notion of phases of matter. So for those of you who perhaps have a bit less physics background, you may not readily think of what a phase of matter is. Well, we are used to classifying different types of systems according to the kinds of physical properties that they have. And these types of classifications we often call different phases of matter. So the most famous example is to think about solids, liquids, and gases as being different phases of matter because they have different physical properties. So you can tell the difference between the solid, the liquid, and the gas. And this is one thing that we love to do as physicists, and a huge amount of physics is about thinking about different phases of matter and thinking about what are the essential properties of each phase. And what I want to do is to think about just solids, and I want to organize solids according to electrical properties. And that is going to bring me back eventually to the idea of topology. So for the moment, let's just put topology to one side. Let's now just think about how we would organize solids by electrical properties. So how can we understand and classify the different possible electrical properties? Well, what you might think of doing is, if you're an experimentalist, you would say, well, I will set up a little circuit in my lab, and I would put a little light bulb in the circuit, and I would put a battery in the circuit, and I would have 2 junctions. And in between those junctions, I would put the material that I want to test. So the gray is just the block of material I care about. And we want to ask, if we put a particular material there, does the bulb light up or not? That is testing the electrical properties of the material, of the solid. Okay, so what you're aware of is that there are certain types of materials, I'm sure, that are insulators. And so in an insulator, in a cartoon picture, what's trying to happen is that you're trying to push the charges into the material, because of course it's the flow of the charge that's the current that allows you to light up the bulb. And you're trying to push the charges in, but there aren't any states for them to go into. They can't go into the material. And so you don't get any current flowing and the bulb does not light up. So I hope you're all very familiar with the idea that many materials are insulators. So that sounds like one kind of class of systems. That's one way that you could classify your solids. You could say, well, we've got insulators. And then we've got conductors. So conductors, on the other hand, allow the charges to flow freely. And so here, this is just a cartoon trying to show that I have my charge carriers just flowing freely across the material, and that allows the bulb to light up. And that is probably what you're most familiar with. Okay, maybe you could think about semiconductors or things like that, but broadly speaking, the conductors and the insulators are the different types of solids that we're used to thinking about in terms of electrical properties. Now, the whole point of this talk is to really tell you about something a little bit different. And that's what we call a topological insulator. And actually, more specifically, what I'm mostly going to be talking about for experts are quantum Hall insulators. So I'm using topological insulator in the broad sense of the term. And I will explain to you a little bit about what quantum Hall is, and I'll explain to you what this type of insulator is. Essentially, my cartoon picture is that this is another type of system that's not quite the same as the insulator we saw before, and it's not the same as the conductor we saw before. And the credit for first discovering a material that behaved like this goes to Klaus von Klitzing, who won the Nobel Prize for this discovery back in 1985. And essentially, the way that we can understand this material, the way that I want to describe this material, is as a block, and it's a two-dimensional block. So you're assuming that your particles are only moving in 2 dimensions. And in the center of this block, it's an insulator. So charges are not able to get into the interior of this material, but they can travel around special little channels around the outside of the material. And these channels are confined just to the edge. So these channels are effectively one-dimensional channels that just go around the edge. And so what you can see here is that if I go back a bit, the conductor can actually take quite a large amount of charge across of it because all the charge is going through the whole bulk. Whereas here, the charges have to kind of wait and go around each other. So, there's only a small amount of charge that is flowing along the edge. So the amount of current that's flowing is very small compared to the conductor. So it's still basically an insulator, but there is this charge flowing, and the charge is only going around the edge. So it's insulating in some senses and conducting in other senses. And the really cool thing about this material is that this edge state, what we call this edge channel, is actually only one way. And I tried to show that by having my little arrows. Okay, so these, what you've got to imagine is there's this material and there's this way for charges to flow, way for the current to flow, but it can only go one way. And to see why that gives you something quite different, imagine reversing the battery. So if you reverse the battery for a conductor, your charges all flow, and they flow now from left to right, whereas before they were flowing from right to left. But you still have completed the circuit and you've got this nice circuit. Now, if we imagine doing that with our topological insulator, the current also flows, but it flows around the top edge of the system because that was a one-way street. So you can think about this as like if you're in a car and you're going on a one-way system and you have got from one building to another building, one street to another street, and you want to go back, you've got to go a different way around the one-way system. And that's what is happening in this material. And that's very cool because if we now add some defects to your material, so this is a little cartoon of a defect, and I'm imagining that my charges are moving along, and then some of the charges are getting reflected by the defect. They just bounce off the defect and they get scattered backwards. So they're not getting through the material. So there's less current getting through. And so if you're measuring, then you're going to see that there's not quite as much current because your material is not as clean. There's more scattering. Whereas if you've got defects and you've got this one-way system for your charges, then your charges are coming around, but there's nowhere for them to go backwards. they can't go backwards because they can't go into the bulk because the bulk is insulating. There's no way, they're not allowed to go into the bulk. There's no states there for them to go into. But they're also on this one-way system. And so they can't reverse in the one-way system. They've got to keep on going. So they've got to go around it. And so what that means is that even if there's defects, even if the edge you deform a lot, even if you change exactly the shape of your material and you make it look really different, because it's just a one-way street that goes around the edge, the current that's carried is robust. So it's a small current, because as I said, you're not getting as much current going through as you do with the conductor necessarily, but it's very, very robust. You can't disrupt it. And that's why it's very cool. Okay, and we'll come back to that in a minute. But at the moment, I've just shown you some pictures. But where could this physics come from? Like, how could you get something that actually behaved like this? So what I want to do next is to take a step back and think about a simple classical model in which you would get this sort of physics. So essentially in something where in the interior of the system, the particles don't move very much, and at the edges of the system, the particles can bounce along the edge one way. Okay, so how could we ever get this from classical type of physics? Well, let's come up with some rules. And the two rules I want to give are, firstly, that my particles are always moving in anti-clockwise circles. Okay, the fact that it's anti-clockwise is not so important. If it was clockwise, then I would just get, you'll see I'll just get the motion in the opposite way. So my one-way streets will reverse direction. But to be consistent with the cartoons I've shown you so far, I'm going to assume that particles are all moving anti-clockwise. Okay, so my little particles are moving anti-clockwise. And the second rule I want is that these particles will bounce elastically off any walls. So if they're near the edge of a box or near the walls of a box, they will bounce elastically. So they will, when they hit the wall, their momentum reverses and their velocity reverses, and then they go off in the new direction. So what does that mean? So if we combine these two rules, that particles must move in anti-clockwise circles and that particles bounce elastically, what will happen if we have a particle near a wall? Well, you can see here that we've got these particles and they're trying to go in these anti-clockwise circles, but then they hit the wall and the wall reverses their velocity. So then they are going in the top half of the anti-clockwise circle again, or the bottom half of the anti-clockwise circle again, depending on whether they're the top or the bottom wall. So I'll just play that, if I can, once more to give you another chance to see that. So you can see here that depending on whether your particle is hitting a wall above it or below it, it ends up moving in a different direction. So that's shown by these arrows. So if your particles are bouncing and they're trying to go up, but then they hit the wall when they're going up, then they're going to end up moving in this direction. Whereas if they're going on top of the wall, they move in the opposite direction. And so actually you can convince yourself that these two rules are what you need in order to have a system that looks where the particles are going classically looks a bit like this. So in the interior of the system, if you're far away from a wall, you're just moving in an anti-clockwise circle. So you're not really going anywhere very much. You're staying just within your circle. If you're at the edge of your system, then you have to bounce, you end up bouncing or skipping along these edges. And that is a one-way system because you're always trying to move in these anti-clockwise circles, but you're bouncing off the walls. Okay, so hopefully you get the idea of that this is kind of a classical model that has that kind of physics that I was just mentioning. Now, what kind of classical system could this be? So I've told you some rules, but what physical law could get you to that? So this is something that maybe those of you that are third or fourth years maybe you already have an idea. And the idea, I hope, would be, for instance, taking a charge and putting it in a magnetic field. Because if we think about what a charge in a magnetic field does, then the force, there's a magnetic force acting on a charge, a moving charge in a magnetic field. And that magnetic force is given by something we often call the Lorentz force. And it's given by Q and then V cross B. So for those of you who aren't doing physics degrees at the moment, you may not have seen something like this. But the essential idea, if you want to know where the force is acting, is we can use something called the right-hand rule. And what we need to do is we need to align our thumb is going to point in the direction of the force that's acting on the particle. If we point the first finger in the direction of the velocity and the second finger in the direction of the magnetic field. So the little crosses here mean the magnetic field is going into the page. So if I go, my magnetic field is going into my page. My velocity, for instance, is going in the plane. And what you can convince yourself of is that that means that my magnetic force is always, is constantly changing its direction, but it's always kind of going radially as I go in this orbit. So what it's doing is as my particle tries to go forward, there's a force pulling it to the side, which causes it to turn into this anti-clockwise circle. And so that's why particles' trajectories bend in the presence of magnetic fields. And so that is the physics that would get you the model I just showed you before. So you take your system, you put it in this magnetic field, and that will give you these kinds of orbits. So that's a classical model that would give you something that looked a bit like these topological insulators I was telling you about. Now that sounds great, but okay, so now can you hear me again? I'm assuming so. So, great.
Sorry about that.
No problem. Okay, so where was I? I was talking about this classical model. And the thing is that that classical model gives us the right sort of physics. However, this itself is quantum physics. And how can we see it's quantum physics? Well, let's actually think about what current we're getting. So we apply a voltage, we apply a certain amount of voltage, and then now we're going to be quantitative, and we're going to say, how much current do we actually measure? So before I was just saying, does the bulb light up or not? Now I'm actually going to apply a certain amount of voltage and measure a certain amount of current. Now, current, you will know from Ohm's law, is the voltage over the resistance. And equally, I could, instead of talking about resistance, talking about something called conductance, which is just defined as 1 over the resistance. And for reasons that you will see, it just is more useful for me to talk about conductance than resistance. But equally, you know, they're just inverse of each other, so I can just always take 1 over and get to the other one. So current equals voltage times conductance. So if I apply a particular voltage and I measure a particular current, and then I take the ratio of those, that will tell me about the conductance, so how the charge is traveling through this material. And what it turns out is that these materials, these topological insulators, these quantum Hall insulators, have very particular conductances. And in the simple case that I'm showing you here, the cartoon that I'm showing you here, the measured conductance would be E squared over H, where E is the electric charge and H is Planck's constant. And the fact that it depends on Planck's constant is really what tells us that this is all quantum physics, because Planck's constant is the length scale of quantum physics. So Planck discovered this when he was thinking about the quantization of light and matter, and he won the Nobel Prize in 1918. And Planck's constant, as you can see here, is this very, very small number. And essentially, why it sets the length scale of quantum physics is because if we think about the wave-particle duality that you know or may have heard about, this idea that at the quantum level particles have a wave nature as well as a particle nature, then that wave nature is associated with a wavelength, and that quantum wavelength is set by h, Planck's constant, over the momentum of the particle for massive particles. And so if you imagine that h is actually not a constant, but something you could change, then if you made h, for instance, much, much larger, you would see that that suggests that the quantum wavelength could be much, much larger. So that's the sense in which I mean that Planck's constant sets the scale for quantum physics, and it comes in crucially to all of our quantum equations. Just as an aside, people have spent some time thinking about what would happen if Planck's constant was larger. If you haven't seen them, then these books by George Gamow, the Tompkins books, are very nice because they try to explain quantum physics in a very accessible way. And what happens is that Tompkins listens to these lectures about physics, and then he has dreams where he imagines how the world would look like if some of these physical things that he's heard about in the lectures were more easily observable on a macroscopic scale. So one of his dreams is, what would the world look like if h, Planck's constant, was a lot larger, and so quantum wavelengths were a lot larger. And so here, this is a little cartoon of him imagining the antelope being having a quantum wavelength which is as big as the size of an antelope. And so when the antelopes come to these two gaps in these hedges, they diffract and interfere just like the double slit interference that you get from waves or for electrons. Okay, now this is intended as quite a nice little book, but actually people have thought about it a little bit more seriously, and there's quite a nice article that I found the other day which discusses exactly, where Planck's constant appears in the equations that we're used to, and how those equations and how the phenomena associated with them would be different. Okay, that's just an aside for those of you who are less familiar with Planck's constant. And to return to what I was telling you before, the fact that Planck's constant has appeared in this conductance has shown us that this is actually quantum effect, these topological insulators, this conductance around the edge in these one-way streets is coming from quantum effect. And this E squared over H is actually, neglecting spin, a quantum of conductance, because you can see it just depends on these fundamental units, the E and the H. Okay, so I have neglected electron spin. Often this has a factor of 2 to take that into account, but in this case, that's fine. And it's the quantum of conductance because you can see it's this kind of like fundamental unit of conductance. Like if you were just taking some the fundamental constants and trying to combine them in such a way to give you a conductance, this is something that you could do by even just by dimensional analysis. And it can be shown that this is actually the conductance that a 1D quantum channel has, provided that all the electrons that enter the channel get transmitted. So as long as you can neglect electron scattering backwards, all the backscattering, then the conductance is of a 1D quantum channel is actually given by E squared over H. So what this suggests is that actually my classical model of particles in a magnetic field is not quite good enough, that I need to make this a quantum model because it's a quantum effect. So one way to do that is, for instance, to take a model of charged particles like electrons in 2D and to put them in a suitable out-of-plane magnetic field. And actually, that is all you need to do to start getting this physics out of your equations. So for those of you that are 3rd and 4th year physicists, you may have solved the Landau level problem for particles in magnetic fields. And actually, Landau levels have exactly this behavior. So you only need Landau levels to get this physics. And it's just if you take your Landau levels and you put them in a box, if you give them hard walls, you will get this physics coming out of it. Okay, so I promised that I would get back to this idea of the quantum Hall effect, because this is actually the name given to this type of material and this discovery that Klaus von Klitzing made. And what he found was not just conductance of E squared over H, but actually he found that if he took his system, his two-dimensional electron gas, which is what is happening in this sample on the left-hand side, and he applied a very strong magnetic field and cooled it down to very, very low temperatures, then as he tuned the strength of the magnetic field, what he actually observed was that he didn't just get a conductance of E squared over H, he got these plateaus emerging at successive values of n E squared over H, where n was an integer. So for instance, there's a plateau here for n equals 2 on this graph, and n equals 3, n equals 4. And these plateaus are so precisely quantized and robust that he wasn't looking for this. He had no idea that this would happen. It was really unexpected when he discovered it, but he was able to look at it and go, wow, actually, this is quantized in units that are fundamental in this E squared over H. Okay, for experts, you will of course notice that I've simplified the cartoon quite a bit. Actually, you can see that what he's doing in terms of the measurement on the left-hand side is a more complicated 6-terminal measurement, whereas what I've described to you is what we call a 2-terminal measurement. And actually, in that case, what he's measuring is a Hall resistance or the Hall conductance. But for those of you that don't know what I'm talking about, don't worry about that at all. It's not important. Just for the experts, of course, you know that there's a few more things to say there. So when he first discovered this, it was a real mystery, because it's like, well, you know, where can this conductance, this precisely quantized conductance be coming from? And how is it so robust? Because people repeated the measurements with other samples, with different shapes, with more disorder and less disorder, and they still got these results. So it didn't seem to matter what you did to the system, you still got these beautiful plateaus. And the plateaus are so precise that it allows you to measure E squared over H to about a part in a billion. It's actually one of our best ways of measuring these fundamental constants. It's that precise. And what people realize is that one way to think about this is to think that the n that you're getting here is this number of 1D quantum channels that you have at the edge of your system, and that this is this topological insulator that I've been showing you. So now you can think about organizing your insulators, and you can think about having what we call a trivial insulator, which doesn't have an edge state, the first quantum Hall state with one edge state, with two edge states, with three edge states, and so on and so forth. And so here you can see that the number of edge states is very suggestive of a topological invariant, because it's robust. For that, I can remind you that we saw that, you know, the number of edge states is something, because they're one way, they're not disrupted. So even if you put defects, there's still just that one edge state there, and the particles still have to go in this one-way system around. They can't go backwards. You also have that it's a global property. So you have to look at your whole material to know how many edge states there are. So it's not just that you can look at one part of it, you've got to look globally, and you see that there's the edge state around the whole of this system. And it is an integer, because you have one edge state or two edge states. You can't have half an edge channel. And that realization that this is actually topological in its nature is one of the reasons that David Thouless won the Nobel Prize in 2016 for topological phases of matter, and that gave us the headlines that we started with today. So this is an example of topological physics. Okay, so we had this notion of the precise quantization and the robustness. And just to say again, you know, this robustness is so good that actually now the quantum Hall effect, these topological insulators, are how we have redefined, or part of how we have redefined standard units. So the SI units. So anyone who's done any physics will know about SI units and how we have to use these. And we've all know a lot about kilograms, So kilogram, of course, is the unit of mass. And the old way that we used to define a kilogram was actually in terms of this block of material that was kept in a bank vault. And the problem was that this was not a very stable way, it turns out, to actually define a mass, because over time, this material is changing a little bit. And so the mass was actually varying. So what people realized is that they needed to redefine this and other units in terms of more fundamental constants. And there is a way that is a little bit complex, so I won't explain, to define mass in terms of h, relate mass to Planck's constant. And then if you want to think about Planck's constant, how do you define Planck's constant? Well, one of the best ways that we have is by thinking about quantum effects such as the quantum Hall effect and something else called the Josephson effect. And by combining those very, very precise measurements, you can get to your best possible definition of h, which in turn can be your definition of the kilogram. So that's just to say that actually this phenomenon, the cool thing about it is that this is this quantum phenomenon that's so robust, it's fundamentally redefined the units that we use. So just to come back then, a topological physicist is somebody who cannot tell the difference between these two types of topological insulators. So just as the topologist doesn't know about the difference between bagels and coffee mugs, to me, these two things are the same. You can change your material, you can deform its boundary a lot, you can make it very, very different, but as long as there's just that one-way edge state, then it's the same type of material. It's the same class of materials. And it has that beautiful, robust conductance. Okay, so for some of the fourth years, very quick slide just to show you that there really is a lot of stuff going on here. I've just shown you some cartoons. The real way that we often think about this is in terms of the properties of the electronic energy band. So if this slide means nothing to you, don't worry about it. If you're a fourth year maybe, or third year, you may understand a little bit more about this. So essentially, if we have an electron in a lattice, we can think about using Bloch's theorem, we can think about the Brillouin zone, we can think about Bloch eigenstates, and then from Bloch eigenstates, those U's, we can ask ourselves, how do Bloch eigenstates vary as we move a little bit in the Brillouin zone? And that gives us this concept called the Berry curvature, which is this omega, and actually this Chern number, which is the number of, it turns out, the number of edge states. So the number of edge states is the Chern number, and that Chern number you can calculate in this way from integrating the Berry curvature. So really don't worry about that if that is not something that you understand, but that's just to show some of the experts that there is a rigorous way of doing all of this. Okay, but why do we care nowadays? So I've only got a few minutes left, so I'm gonna switch up my speed now and go quite quickly, because I'm just flashing a few things for those of you that are interested to start thinking about, or maybe ask a question about. So why do we care? Well, because nowadays we understand that topological physics and these topological phases of matter, it turns out, aren't just really about electrons moving in solids. There are analogous things, analogous topological edge states that we can find in all sorts of systems, ranging from cold atoms, which is where I work, and photonics, which is my area as well, through to even classical mechanical systems, electrical circuits, and acoustics. So topological phases of matter has now become this very broad area that isn't just about electrical properties of materials, but is about these edge states, these edge channels in a much more general sense. It's also not just quantum Hall. So what I showed you was actually what we call a quantum Hall insulator, but there are other things. There's things called quantum spin Hall, where you also have the fact that the electron has spin. There are things that happen in 1D or in 2D. What I showed you was something that was like a, 3D. What I showed you was a 2D phenomenon. And there are other very cool things called topological superconductors, which are exciting because they can have excitations, so they can support modes, which are called Majorana modes, which are these very weird things that if you braid them around each other, you don't get back just to the same state, you actually get back to a different state. And that's led to something, proposals for something called topological quantum computing, where the idea is that you can use your anyons, your Majoranas, or however else you've got them, in order to kind of do computing in a more robust, error-tolerant way. And that's one way that maybe in the future, topological phases matter could actually be useful. The other thing is to say that because we've got this very robust one-way channel around the edge of your system, that's kind of the whole idea that I've been trying to explain to you, that could lead you to applications where what you want is not necessarily to transmit lots of light or lots of electrons or lots of whatever particle you're trying to carry, but you just want to transmit it in a very, very robust way. And that's something that has got people interested from the side of thinking about photonic devices for the future. So as I said, I'm not really explaining these concepts. This is more just giving you a flavor for some of the things people have been interested in. And I just want to spend the last 5 minutes thinking about the area, or telling you a little bit about the area that I'm really been working on. So everything up to now is stuff that other people have been doing in the field. And now I want to tell you a little bit about something that I care about, which is that we can extend these ideas up to higher dimensions. So what I was telling you about was a 2D system where you've got a 2D insulating bulk and then a 1D channel. Now in 3D, you can also have topological insulators, and there you would have a bulk that is insulating. So now that's a 3D bulk. And if you think about what the edge of a 3D system is, it's all the 2D surfaces. So if you have a cube, it's all the faces of the cube. And that gives you a 2D surface. So each of those faces is 2D. Now, the cool thing is that people have gone further, and mathematicians have predicted, mathematical physicists have predicted that there are topological insulators that happen in 4D and higher dimensions. So by 4D, I mean 4 spatial dimensions plus time. So not 4D space-time, but actually having 4 dimensions plus time. And that now the bulk of your system is this 4-dimensional bulk, which, okay, is very hard to visualize, but you can, okay, there's a 4D bulk. And the surface of a 4D bulk is 3D. So just as the surface of a 3D system is 2D and the surface of a 2D system is 1D, the surface of the 4D system is 3D. And that 3D volume would now be conducting. And so people have kind of predicted these kind of 4D systems. And what got me interested was going, you know, how on earth could this actually happen? Is there any way that we could ever imagine to simulate something that has 4 spatial dimensions, given that we are used to just 3 spatial dimensions, and we don't have any 3 spatial dimensions? And it turns out that people have developed some tricks to do this. And I will explain to you one of those tricks. So in the interest of time, I'm not going to be able to tell you a lot about it, but I'll just give you a flavor of one of those tricks. And to get that flavor, I'm going to start by just saying, what do I mean by a spatial dimension? Well, I'm a theoretical physicist, so I think in quite an abstract way. And what I mean is just the number of coordinates that you need to find where something is and how many directions you can move in. You know, so in 2D, for instance, you can move in X and Y, and you need 2 coordinates. You need to know which, for instance, row or which column you're in this material. In 3D, you have 3 directions. So you can go X, Y, and Z. And of course, you need 3 coordinates. So for a theorist, it's actually quite easy to think about 4 spatial dimensions, because we think about a system that has got 4 coordinates. So we allow our equations to have 4 coordinates, and we allow our particles to move in 4 separate directions. So we say we can move in X, in Y, in Z, and some hypothetical 4th dimension W. So what we would need to simulate a 4 spatial dimensions would be to have some way that particles can move not just in X and Y and Z, but also in some extra synthetic artificial dimension, in some extra artificial way. And that's something that people have actually come up with very recently. So this goes back to a proposal that came from a group in Barcelona in 2014. And what they were pointed out was that if we're thinking about, for instance, atoms, then you can have an atom that moves in X, Y, and Z, you know, the atom's just moving around, but the atom also has internal structure. So this is just a very simple example of hydrogen, where you've got a nucleus and you've got the electron. And as you know, the electron occupies certain electronic orbitals, certain electronic energy shells. And in the ground state, the electron wants to be as close as it can be to the nucleus, because it's negatively charged and the nucleus is positively charged. So the electron wants to sit in the lowest of these energy shells. But that's not the only thing that can happen, because if you shine light on the system, you can give the electron energy, you can boost it up, you can excite it so that it jumps to, say, a higher shell. And if you shine more light, you can give it another quantum of energy such it jumps again. Equally, your electron can fall back because, of course, it's at higher energies, and you can stimulate its emission back to a lower shell, and then it will emit the extra energy as light, and it will fall back again, eventually all the way to your ground state. And so what these people pointed out was we could maybe interpret these different states as being different sites along a synthetic dimension. So thinking now about the atoms moving in X, Y, and Z, but also there being this internal state dimension, and that as we're shining light, so we shine light all the time on the atoms, and that causes the atoms to move up and down this synthetic internal state dimension. And so now it turns out that actually the equations you write down to describe this process, so describing these atomic transitions, is analogous to how a particle, you can think about a particle hopping on a lattice, so moving around on a lattice. And this has been successfully realized in experiments, at least to go from atoms being able to move in one dimensions and then adding this synthetic dimension so that then you can sort of see 2D like physics. So you use this synthetic dimension. And it's not actually hydrogen that people use. They use much more complicated structure, atomic species such as rubidium, ytterbium, or dysprosium, where the electronic structure is much richer. But the essential idea is this idea. And there are many other ways, it turns out now, to actually do this in photonics and cold atoms. And that's something that I've been working on and I'm very interested in. So how can we use this, different types of internal states to mimic a spatial dimension? Because the equations we get to are the equations that we're interested in. So one thing that I did with some collaborators a few years ago was to propose how we could use this idea to make a 4D topological insulator. And this was a picture that we just drew. So the idea is that you've got these atoms, the idea that the atom can move in X, Y, and Z, but it can also, its electrons can also move between these different orbitals, which is what we call moving in the fourth dimension. And no one's yet been able to do that in the lab, but we hope they will soon. We've actually got other ways of simulating dimensions, which I don't have time to tell you about. But if you're interested, you can check out this feature article, which was written about the research going on in the field about how people are now building higher dimensions. And it's all wrapped up with this idea that we want to get to realize 4D topological phases of matter and other topological phases of matter. Okay, so I've told you a little bit about these topological phases. And what are we trying to do? What are we still trying to do in this field? Well, we're still trying to figure out what else we can learn from topological ideas. So actually, people are still coming up with new ideas of how topology relates to physics. We want to create new types of topological phases of matter and discover new types of phases. We want to make it useful. So as I said, the redefinition of the SI units is a great example, but can we find other good applications? And there are many, many things that I haven't talked about, for instance, including strong particle correlations and the cool stuff you can get that happens when particles interact. So with that, I just want to thank you all for your attention and to thank the organizers again very much for the invitation to talk. And best of luck with the exam.
Okay, thank you very much, Dr. Price. So far, we've only got one question in the chat, but it does seem like a good one. It came from Robin Burton, who was asking, can you give an example of how these quantum conducting channels are made? Are they just found in materials, or do you have to sort of artificially create them to produce these topological insulators?
Yes, that's a great question. So they emerge. So you don't make them. What you need to do, so the example that I was giving of the quantum Hall system, for instance, what you need to do is you need to just create a system in which your electrons can only move in 2 dimensions. And once you do that, and you apply a strong enough magnetic field and you cool down to low enough temperatures, those channels will emerge naturally through the quantum physics. So if you're thinking as a theorist, then what I'm basically saying is, if you just take electrons and you write down your equations, your Schrodinger equation for your electrons in a 2-dimensional system, and you introduce a magnetic field, so you couple them to a magnetic field, and you solve the Schrodinger equation, and you solve it with boundaries in a box, then you will find those edge channels just from the solutions of that Schrodinger equation. So it's something that is a consequence of the quantum mechanics. So what you need to do, though, as an experimentalist, is to first get to the stage of having a nice 2-dimensional gas of electrons. And to create that, you need special devices. So in that case, they had to build something called a semiconductor heterostructure. So they had to make quite a complicated device in order to get it so that the electrons were just moving in this 2-dimensional plane. But once he did that, and once he applied a strong magnetic field, those edge channels just popped out. He wasn't looking for them. He discovered them.
Okay, fantastic. Thank you. Are there any other questions from participants? Okay. So the first question we have there, again, unfortunately, I'm very sorry, I can't pronounce that name, comes from Tomas, who's saying, how analogous is the number of layers to the number of topological holes in a subject, in a material, sorry?
So this is a very good question. So the number of channels is a topological invariant, and it's not quite the same mathematically as the genus of a surface. So it turns out that actually the number of holes that I was telling you about is one type of topology. And there are it's definitely analogous. The number of channels that you can get is definitely analogous to that, but mathematically speaking, it's a slightly different structure. So it's actually related to these things called Chern numbers. So in mathematics, there's the genus, and there's also things called Chern numbers. And this is actually related to Chern numbers rather than to the genus. But you can kind of still think about it quite similarly. So for instance, one way to think about it is that if you think about how you count the number of holes, what you can do is you can kind of look how the surface bends everywhere. And then if you know how the surface bends and you know how the whole surface bends, then you can figure out whether there's a hole or not, because you've mapped out what the surface is doing. And that's something similar to the equations that I flashed up very briefly for the experts, where I was talking about how the eigenstates, the block eigenstates, are changing. And if you look at that globally, you get to something called the Chern number. So it's difficult in the sense that there's no hole that I'm not talking about holes in the physics sense, in the physics picture at all, but it is analogous to the number, to a whole thing. So I'm afraid that that's about as good as an explanation I can give right now, but it's a great question, and there's a lot of mathematics there to go at.
Excellent. Thank you very much. I think we're going to leave it there just to ensure that we're on time for the the
Of
exam
course.
at 10:30. Thank you very much for giving that fascinating talk. It was very engaging. And yes, thank you very much for your time.
Thank you, and good luck, everyone.
Great, thank you. Thank you again for joining us. It's been really great to have you. So we are going to move on to the exam now. Anthony has been assigning you all to your breakout rooms, so he is going to talk a little bit more about that. But good luck, everyone. I hope you enjoy it, and yeah, see you on the other side.
Hello, everyone. If you have not already renamed yourself as your name and your team name, please do it now. I have 1, 2, 3, 4, 5, 6 teams that have not got any members, 7 teams that have not got any members in. So please, 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 please do it now. We are going to start just 2 minutes later for the exam because there's already been a correction to the paper. So it's a good start. So please,
Sorry
please,
about that.
that's okay, James. Please, if you haven't already done so, rename yourself. And thank you to everyone else that has. Great. Right, people are adding in now. Right, I just need to change the exam.
Also, thank you to everyone that joined us that is not participating in the exam. You can join us back at 3:45 for our next public talk, which will be by Professor Lahal. So we hope to see you then. Have a nice intermediate time. And as for everyone doing the exam, get ready and good luck.
Okay. James, I'm going to send you the new version to upload in a second. And I'm just adding in the last few people. It's good that everyone starts at once. Okay, James, I've sent that to you now with the new version. Okay, let's just upload, make sure the last few people are in. Once again, if you haven't already, make sure you put your team name. Oh, great, there's about 50 people to assign. Wonderful start, isn't it? If you did have any questions, now's probably a good time to ask them. I know not everyone was here for the beginning talk. Okay, there's no one from that team here yet.
Ready when you are, Anthony.
Okay, I'm just assigning the last few people. Okay, they've all arrived now. Anyone that is not participating in the exam, probably be a good time to leave. So I don't start bombarding you with questions of why you haven't renamed yourself eventually. And there's a Bay Area Boys. Okay, and just a few more people, and then we're ready to go. Oh dear.
If you are a member of the public, not part of the exam, be sure to come back at 3:45 for the next lecture. If you are for the exam, stay on. We'll be starting shortly.
Okay, all right, okay, now they've actually got a team member. That's good. Because why not? We're good that we have a break because this can dig into the break time. The exam end time won't change. You'll just have less of a break. So the first part of the exam I will time for 2 hours. As of when we start. You're part of that team. And you're Bernoulli. You guys are Twiggery and you are a Dark Fan.
Anthony, do you mind pausing the stream?
Yep, once I've finished assigning everyone, which is
Excellent.
not now because someone else has just joined. The minimal potential.